Imagine a breakthrough that flips a long-standing energy loss problem on its head and turns it into a powerful advantage. This is exactly what Dr. Dong-Soo Han's team at the Korea Institute of Science and Technology, KIST, Semiconductor Technology Research Center, has achieved. Working alongside Professor Jung-Il Hong from DGIST and Professor Kyung-Won Kim at Yonsei University, they have uncovered a fascinating principle that transforms what was once considered spin loss, a frustrating waste of energy in magnetic systems, into a novel source of power to control magnetism. But here's where it gets controversial. What most researchers saw as a limitation is now being harnessed as a key asset for next-generation technology. Spintronics, which exploits the intrinsic spin of electrons rather than just their charge, is rapidly emerging as a foundational technology for future information processing devices. Unlike traditional semiconductor electronics, Spintronics promises ultra-low power consumption and enhanced non-volatility. This makes it especially attractive for applications like memory storage, neuromorphic computing chips that mimic brain function, and devices designed for stochastic, probabilistic computation. The team's discovery is hugely significant because it introduces a fresh angle for boosting the efficiency and sustainability of devices reliant on electron spin. The researchers discovered a remarkable physical behavior where magnetic materials can spontaneously change the direction of their internal magnetization, essentially the magnetic orientation, without needing any external triggers, like magnetic fields or electrical pulses. This is no small feat, considering that magnetic materials form the backbone of data storage and computation. Typically, the up magnetization state represents a binary 1, while down stands for 0. Switching between these states is how magnetic devices encode information. Normally, flipping this magnetic state requires forcing electron spins into the magnet with a substantial electrical current. However, this process traditionally causes something called spin loss. A portion of the spin current fails to reach the magnet and is lost as wasted energy. For years, this spin loss has been seen as a major culprit behind the inefficiency and high power demands of spin-based devices. The conventional approach has been to painstakingly design materials and fabrication techniques to minimize this loss. Yet here lies the fascinating twist. The KIST-led team found that this spin loss isn't just a problem to be eliminated. Instead, it actually triggers a spontaneous shift in magnetization by itself. Picture it like a balloon deflating and pushing air as a reaction. Spin loss acts like that air escape, causing the magnetic state to tip over naturally. Their experiments revealed an almost paradoxical effect. The greater the spin loss, the easier it becomes to switch the magnetization, meaning less energy is used overall. What does this mean in practical terms? The energy efficiency for switching magnetization can be improved by up to 3-fold compared to traditional methods. Even better, this enhanced efficiency doesn't demand exotic or complicated materials or device architectures, which makes it an exceptionally viable solution for industrial applications. The simplicity of the device design also means it fits neatly with existing semiconductor manufacturing processes, paving the way for high-volume, cost-effective production. Moreover, this approach is excellent for shrinking device sizes and integrating high densities of components. The potential applications span a broad spectrum, including AI-focused semiconductors, ultra-low-power memory modules, brain-inspired neuromorphic computing systems, and probabilistic computing circuits. Given the current momentum in AI and edge computing technologies, the timing of this innovation could not be better to power the next wave of highly efficient, intelligent devices. Dr. Han, who is a senior researcher at KIST, emphasized the paradigm shift by saying, "Up until now, simply reducing spin loss was thought to be the only pathway. We've shown that these losses can be harnessed as an energy source to induce magnetization switching." Looking ahead, the team plans to push forward with ultra-compact, energy-frugal AI semiconductor devices, key building blocks for the AI era's ultra-low-power computing needs. For context, KIST was Korea's pioneering government-funded research institute since its founding in 1966. Dedicated to tackling national challenges and driving innovation, this groundbreaking work was made possible with support from the Ministry of Science and ICT, the KIST Institutional Program, and the National Research Foundation of Korea, among others. Their findings were recently published in the prestigious journal Nature Communications, recognized for its impact in the scientific community. But here's the question for readers. Is it truly time to embrace what was once considered waste as a new source of power? Could this counterintuitive approach redefine how we think about efficiency in spintronics and beyond? Or does relying on loss as a mechanism risk unforeseen challenges down the line? We'd love to hear your thoughts and debates. Do you agree with turning spin loss into a beneficial energy source? Or do you think this raises more questions than answers?